Hello guys, hope you're doing well, and as always, if you are new to my channel, I would request you to subscribe to my channel so that we shall be able to watch all the latest videos that I will be uploading on my channel. Okay, so the problem at our hand today is that we have a bucket that has a weight of 80 pounds and acting in the direction of positive z-axis, and there are three springs which are being forming a ring at point A and being attached by means of a hook. The springs have a stiffness of 50 pounds per feet and they have an initial length of 1.5 feet. Okay, and you need to determine the vertical distance d from rim to point A for equilibrium, and that vertical distance starts from this point and ends at this origin, which is basically this point. And that distance, this is the distance d that you needs to calculate. And now we basically if you look at our FBD for this system, is that we assume, since there are no axes given, we assume that our x-axis is parallel, starts from here and it is parallel to this force C, and this is our x-axis. Okay, we have assumed our y-axis is basically, this is our y-axis we have assumed, and the z-axis is being along the positive z-axis, and we have assumed that this is our positive z-axis. So these are our assumptions because the x-axis is not given, the y-axis and z-axis are not being shown to us, so we can assume. Now the next target will be to calculate the components A, B, C, D points, the coordinates we need to calculate. Okay, so we can say, since our this point C, we will be treating our point, this is point C, this is B, this is D. Okay, and this is point A. So we, from A we assume that our coordinate system origin is A, so the coordinates are 0 0 0. The coordinates for B, C, D are slightly tricky. Okay, so for C, first of all, is more simpler. We can say that this is our x-axis, so we will say that the I component for C will be simple 1.5i, and since this C is lying on the x-axis, it will not be moving along the y-axis, so it will be 0. And perpendicular distance from A to this point is basically from C is nothing but D. Okay, and this is D, and we are writing K as a unit vector. I and J are the unit vectors, you already know that. Okay, and for B and D we have to be very careful. Here we know that the angle between B and D is 120, and we also know that our x-axis is cutting straightly along that angle, along the negative x-axis. So we can assume that since the angle is 120 and this x-axis is cutting this angle straight along between 120 degrees, so here we will make an assumption, and that assumption will be that the angle from this point to this axis where this force FB is acting is going to be 60 degrees, and the other angle will also be 60 degrees. We have just projected it and basically divided 120 into two components. Okay, you can see here, if you not clear in this FBD, this angle from here to here is 120, from B to D is 120. So we have just assumed that this axis is going straight and it is cutting it equally between the two. When we assume this, we will say that if this angle will be 60 degrees and this angle is 60 degrees. So now what we will say that this and these are the two components of this angle, which is the 60 degrees. So along the x-axis component of 60 degrees will be cos 60, and the angle which is the component which is opposite to 60 degrees will be sine. So they have all been shown. Okay, that is why when we talk about B, we will say the I component will be 1.5 cos 60i. So again from here if we move along this direction, which is along the negative x-axis, the radius is 1.5 cos 60i. Since it is on the negative x-axis, we will take minus 1.5. And the other component that we will be taking is basically this component. This component is parallel to the y-axis, but if you look at it from here, it is positive y, and this is positive y, this is positive y, this is negative y, so it will be 1.5 sine 60 j, and the same dk will always be the same from here to here. Now we go to the D component. D component is exactly the same, but the only difference is that here, if you look at it, here basically, when we were looking at it, this component was positive along the y, the j was positive along the y, uh, but when we go here, the j was positive along the in the B component. But now, since instead of going here, when we are going to the D point, it will be in this direction, and this direction, if you look at it, is the negative y. So when we calculating d, it will be 1 point minus 1.5 cos 60 I, exactly like this, but this component is 1.5 sine 60 j, but with a negative sign. No, not like b, it was positive, and dk is still the same. So this minus is because there is going to be another basically what is called as an axis in the negative y axis, and if you want, I can just let you, it will be just like this, it will be just like this, okay, and projecting it like this thing exactly parallel to the y axis, okay, it will be parallel to the y axis, this axis, okay. So it will be negative, and that is why we have made it 1.5 sine 60 with a negative sign. Now we know that we are going to need to calculate this d. So d is along the z-axis, it's parallel to z-axis. So if we are interested in calculating d, we have to calculate this component of force. This is our force. If you look at it over here, this is our force, but we are interested in calculating d, so we want this component of force. So this component force could very easily be calculated as, if we take this triangle, this vertical d, then this radius 1.5 feet, and this hypotenuse. If this is d, this is 1.5, what will be the hypotenuse? D square plus 1.5 square, the square root, because we want to take the length. So now if we take the sine component of this, if we take the sine component, why? Because we want a perpendicular d length. So it will be nothing but d over d square plus 1.5 square, and in a square root. Now we know that since there are three forces and we apply sigma fz, so it will be the vertical force along the z-axis is 80 pounds along the positive z, this is 80, and this force F component along the z-axis will be F into d over square root of d square plus 1.5 square. Why we add this 3? We add this 3 because there is one force here, one force here, and one force here. So these three forces will have three components along the z. So we have 3d over square root of d square plus 1.5 square. So this is our main equation is being formed for the whole problem. Now we have to calculate this F. If you look at this photo, this F is made up of three springs, and we know F equals to FSP because of the spring. But what is spring force? K delta X. So now we can do is that what is K? K is 50 pound per feet. Now delta X is nothing but final length minus original length. What is the original length? 1.5 feet. And what will be the final length? The final length will nothing be but the hypotenuse, which is this thing. So we put it over here, square root of d square plus 1.5 square, and minus the original length. Now we have calculated this F. We can do what is put this F in equation 1 here. So if we put it over here, it will be 80 minus all this F, I put it over here like this, multiply by this whole thing 3d over under root of d square plus 1.5 square, and this all must be equal to 0. Now this equation 2 has been completely formulated, and we are ready to calculate d. But we have to be very careful that we have to simplify this equation, okay. So if after you simplify this equation, we get a 4-degree polynomial in d, and this degree polynomial, if you look at it, is nothing but it is d4 minus 1.067 d cube plus 0.284 d square minus 2.4 d plus 0.64 equal to 0. Now we are interested in calculating this polynomial. So you can use your calculator to directly put these constants to solve it. Or what we can do here is basically we can go here in this and we can put the values of those coefficients. And those coefficient values, if you look at it, is basically nothing but minus uh, uh, it will be, sorry, not minus, but again we can put it as 1, and the other one that we put it over here is going to be the value as minus 1.0684, and then the other value that we want to put it here is going to be minus 2.4, and the other coefficient, the last coefficient which we're going to put here is going to be, according to the equation, is 0.64. Okay, so now we have put all those values. We are interested in calculating what are the final value of D. So if you look at it, we get those four values. Okay, these are the imaginary values. We are not interested, and since we are interested, 0.28 to 0.268 length cannot be possible in terms of feet. So we will be taking this value, which is 1.6406 feet. This is going to be our value, and you can see after calculating this quartic polynomial, and you can see this is the value that we have calculated. So this was our problem. It was a tricky problem, and I hope you have understood this problem. So if you have any questions, do let me know. I will be there to assist you in every possible way. Thank you, and you have a wonderful day.